Okay, so just some practice questions to do, mainly to do with the calculations for quantum chemistry, but also there's one where we get to draw something which is fun. So, for example, a pigment is found to have an excitation energy of 3.97 times 10 to the minus 19 joules. At what wavelength will this molecule absorb radiation? What colour do you expect it to be? So that's an interesting twist on it. So energy equals Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the minus 34. So if you divide the energy, so 3.97 times 10 to the minus 19 joules, divided by Planck's constant is equal to the frequency, which is denoted by the Greek letter nu, or which looks like a V, and you get that's equal to 5.99 times 10 to the 14 hertz. Then you can calculate the wavelength. So the speed of light is equal to a wavelength times the frequency. Speed of light is 3 times 10 to the 8 meters per second. So you can do 3 times 10 to the 8 meters per second divided by 5.99 times 10 to the 14 hertz is equal to the wavelength, which is equal to 5.007 times 10 to the minus 7 meters, which is 500.7 nanometers. So any calculation where you're putting it into in terms of visible light spectra, you might want to go to nanometers. It's just a bit easier that way. And then the pigment is, so what color is 500.7 nanometers? Well, if you look it up, it's in the green part of the spectrum. It's sort of on the edge of the green blue part, but it's more green than blue. So what color will it appear? Well, it's absorbing at that color, so it actually is going to appear the complementary color, which is red. So it's important to remember that it's absorbing at the color, so it's actually reflecting all the other colors. So it's reflecting the complementary colors, the complementary color, so it will appear red to our eyes. So that's an interesting example of a calculation using some of our quantum chemistry. Another example of a quantum chemistry equation is what is the energy difference between the n equals 1 and n equals 3 state in helium plus. So helium plus, it has 1 electron, so it's a hydrogen-like atom, and so the change in energy is equal to, you can calculate using the Rydberg equation, so it's the Rydberg constant for hydrogen times the atomic number squared times the difference between 1 on the first energy level squared minus 1 on the other energy level squared. So that's 2.18 times 10 to the minus 18 times 2 squared is 4 times 1 minus 1 on 9 is 4 times 8 on 9 times the Rydberg constant is 7.751 times 10 to the minus 18 joules. So that's the energy difference between n equals 1 and n equals 3 for helium. Helium plus. And finally, I will attempt to draw the 3px orbital, including the node. So, first of all, drawing any orbital, it sometimes helps to put in some axes. In this case, just an x and a y axis will do, x and y. So it's the px, so it's along this axis, and it's the 3px, so it has some lobes in here, and here. This is and then there is a nodal circle around those, and then it is the big nodes out here. So those are of course 3D. So you've got a nodal plane through along the y-axis. Y-axis is a nodal plane. And you've got these two lobes inside a nodal circle, a spherical node in fact, and then you've got the the lobes outside of that. So no one's expecting you to draw perfect orbitals in the exam, but that is what a 3px orbital, sort of the cross section through it along the xy axis, looks like, and that's, I believe, a fair representation.